Number 16. A small pin fixed on the table top is viewed from above from a distance of 50 centimeter. By what distance would the pin appear to be raised if it is viewed from the same point through a 15 centimeter thick glass slab held parallel to the table? Refractive index of the glass is 1.5. Okay. Does the answer depend on the location of the slab? Now see, here the height of the pin which is shifted is nothing but, first of all, real thickness of the slab minus the virtual thickness in the slab. Okay, it is virtual thickness in the slab, we can say. Now see, real thickness is T, that of the slab. Now, as you know that the virtual height, try to understand, virtual height Hi upon original height Ho is n observer upon n object. Try to understand. Now observer is in air, so we can write Hi upon Ho is equal to refractive index of n is 1, and the refractive index of the glass slab which is kept in between the observer and the pin is say mu. Then Hi, try to understand, Hi is equal to Ho upon mu. It is Hi is equal to Ho upon mu. So if this Ho, that is original height or original depth, is T, that of the thickness of the slab, because the pin would be at the bottom of the slab. So the thickness of the slab will be the Ho, that is original height or original depth, upon mu. So imaginary height would be T by mu. So if the real thickness is T and the imaginary height or thickness is obtained to be T upon mu, then the height of the pin which is shifted will be original minus the virtual, that is whatever is the virtual thickness T by mu. So here it is written as T minus T upon mu. T is taken common. Okay. Now rest of the things are very easy. Just we have to place the values. Okay. T, that is thickness of the slab, is given. Thickness of the slab is 15 centimeter. Okay. Then the refractive index is 1.5. Just we have to simplify and you will get the answer, that is 5 centimeter. Okay. So we can say that the shifting will be 5 centimeter, and this answer does not depend on the location of the slab. Wherever you keep the slab, this shifting will be same, that is 5 centimeter. Now 19th one. Okay, the image of the small electric bulb fixed on the wall of a room is to be obtained on the opposite wall 3 meters away by means of a large convex lens. What is the maximum possible focal length of the lens required for this purpose? Now see, as you know that U plus V is equal to 4 times F. Okay. So if you take U, that is equal to V, because both the side of the lens, or we can say the distance from the lens on both the side will be equal, that is u, that is equal to v, okay, and it is equal to 3 meter, okay. So here this will become 3 is equal to 4f, so f will be equal to 0.75, okay. Very easy to understand, okay. It is as such, u is equal to v, it should not be, it should be u plus v, okay, because wherever you keep the lens, say for example the bulb is here and the opposite wall is how much, 3 meter away. So wherever you keep the lens, okay, the image is going to be produced here on this wall. So the distance of object and distance of image, in any case it would be 3 meter. So as you know, u plus v is equal to 4f, and u plus v, it should be u plus v, okay. U plus v will be 3 meter, so f will be equal to 0.75 meter, or we can say here there must be a correction, okay. It must be u plus v, u plus v is equal to 3 meter, so 3 is equal to 4f, so f will be equal to 0.75 meter. Now the next numerical 20. A screen is placed 90 cm from an object. The image of object on the screen is formed by a convex lens at different two locations separated by 20 cm. Determine the focal length of the lens. Now see, when the lens is shifted 20 cm this side, okay, the image is not changing its position. Try to understand. First of all, you should understand this. The lens is kept initially here and then it is shifted here. The image is falling on the screen, so image is not changing its position, or rather screen is not changed. You are shifting the lens from one position to the second position. Now if this distance of object is taken to be x, the separation between the lens, we know it is 20 centimeter. Then if the screen is not displaced, means the position of image is here only, then this distance has to be x, okay. So you can now easily understand x plus 20 plus x is equal to 90, so x you will get 35 centimeter. So object distance is 35 centimeter. If it is on this side, then it is u is equal to minus 35 centimeter, okay. And if you keep the lens here initially, then the image distance, this will be 20 plus 35, so it will be 55 centimeter, and that will be positive. So you have now v is equal to 55, u is minus 35. Just we have to use the lens formula, 1 upon v minus 1 upon u is equal to 1 upon f. Place the values and you get the value of f to be 21.4 centimeter, okay. Now we shall discuss the numerical number 9.21, okay, in my first part. Determine the effective focal length of the combination of two lenses in exercise 9.10. Now first of all, you should remember the data in the 9.10, or just look at the 9.10. If they are placed 8 cm apart with their principal axis coincide, does the answer depend on which side the combination of the beam of parallel light is incident? Is the notion of effective focal length of the system useful at all? Now if you see in the previous numerical, then in that you will find that focal lengths are given 30 centimeter and 20 centimeter, okay. Just look into the 10th, what is the focal length of a convex lens of 30 centimeter, okay, in the contact with concave lens of 20, so f2 is negative. Distance between them is 8 centimeter. One is convex, the other one is concave. Okay, distance between them is 8 centimeter. Okay, now if parallel rays incident on first lens in absence of second, what will happen? They are coming from infinity. Focal length f1 is 30 centimeter. Okay, so the image will be formed on focus, and that will be at 30 centimeter from the convex lens. Okay, so at 30 centimeter somewhere here, okay, this distance would be 30 centimeter, and here the image will be formed. Now if there is a presence of this lens, okay, which is 8 centimeter apart from the convex lens, then this image which is formed behaves as object for this lens. Now try to understand what is the distance between these two. Naturally this will be 22 centimeters. So this will be the object distance for the concave lens. So object distance will be UE for the concave lens, and that will be 22 centimeter. It is on right hand side, so it is positive. Focal length is negative. Now image distance 1 upon f2 is equal to 1 upon v2 minus u2. 1 upon v2 can be made as a subject of formula. Substitute the values, simplify. You will get v2 to be minus 220 centimeter. Okay, so parallel rays converge at 220 minus 4, that is 216 centimeter from the midpoint of the system of two lenses. Okay, this is for the reference only. If you have this kind of combination, okay, and the distance between these two lenses is 8 centimeter. Okay, so midpoint will be at 4 centimeter, and here the final image is formed at what distance? It is finally formed at minus 220. Try to understand. Minus 220 means the image will be on left hand side. Okay, somewhere here the image will be formed 220 centimeter from this lens. So from the midpoint, okay, this 4 centimeter has to be subtracted. So it will be 216 centimeter from the midpoint of the system of these two combination of two lenses. Now we take second case. Let the parallel beam first incident at left of concave lens. Okay, concave lens we are having. Okay, so that concave lens is having minus 20 centimeter as its focal length. Okay, it is lens only. So the image will be formed at what distance? Okay, that you can easily calculate. 1 upon f1 is equal to 1 upon v1 minus u1, so 1 upon v1. Okay, so we can easily calculate that image is formed at minus 20, and that will behave as a image for the second lens. Rather, we cannot say image, but it will behave as an object. This image will behave as a object for the second lens, and distance will be minus 28 centimeter. Try to understand. First we have now concave, and now we have convex. Distance between them is 8 centimeter. Image is formed at minus 20 centimeters somewhere here. This is the image. So this image will behave as an object. So this distance between the convex lens and the image which is behaving as an object will be how much? It will be, because this is 20, this much is 20, and this 8, so total will be 28. Okay, now using lens formula, okay, for the second lens 1 upon f2 is equal to 1 upon v2 minus 1 upon u2. Just we have to substitute the values. Okay, f2 is 30, the other one is minus 28. to simplify, you will get V2 as minus 420 centimeter. So the parallel beam appears to diverge from a point 420 minus 4, that is midpoint is subtracted, that is 416 centimeter on the left of the center of the two lens system. From this above two calculations, we can conclude that answer depends on which side of the lens system the parallel beam is incident. Whether it is first incident on convex and then on concave, or on concave and then on convex, it depends. So the notion of effective focal length is not useful for this particular case. Okay. Now see, an object 1.5 centimeter in size is placed on the side of the convex lens in the arrangement first above, right? The distance between the object and the convex lens is 40 centimeter. Determine the magnification produced by the two lens system and the size of image. Okay. Now u is minus 40, f is positive 30 for the first lens, that is convex lens. We can easily calculate 1 upon f is equal to 1 upon v minus 1 upon u. Okay, you can find the value of v1 to be positive 120. Okay, so magnification by the first is 120 upon 4, so it will be 3. Okay. Now the image which is formed by the first lens will behave as an object. Okay, so the image is a virtual object for another lens. Okay, and it will be at what distance? Okay, try to understand again. First we have this convex lens, okay, and then we have the concave lens. The image formed from the convex lens is at 120 centimeter. Now distance between them is 8 centimeter. So this distance will be 112 centimeter, that is the object distance for the concave lens. So it is 112 centimeter, focal length is minus 20. Now easily you can get the value of 1 upon v2 as 1 upon f2 is equal to 1 upon v2 minus 1 upon u2. Substitute the values and you get minus 24.9 centimeter, and magnification is v2 upon u2, easily it is 0.217. Okay, so this calculation is easy as such. Okay, easily it can be obtained. Okay, it is 1 upon v2. Okay, 1 upon v2 is obtained, that is in this particular calculation. Just inverse of it will give you the answer of v2. Okay, it must be v2. Okay, here it should be v2. v2 is 24.9 and those values are substituted, so you will get m2. Okay, now resultant magnification is m1 into m2, that we have already discussed while combination of lens is discussed. So it will give you 0.651, and image height is m is equal to h2 upon h1, that is magnification is height of image upon height of object. Height of image is h2, height of object is h1. Okay, so h2 can be easily calculated, m into h1. Magnification is 0.651 into 1.5. So the height of image will be 0.98 centimeter. Now numerical number 9.22. Okay, at what angle should a ray of light of incident on the face of the prism of refracting angle 60 degree, so that it just suffers total internal reflection at the other face? The refractive index of the material of the prism is 1.524. Okay. Now here from the second phase, it is experiencing the total internal reflection. Try to understand, from the second phase it is experiencing the TIR. It means that this angle of incidence for the second phase, try to understand, angle of incidence for the second phase has to be equal to the critical angle, that is IC. Okay, and as you know, sin IC is 1 upon mu. Okay, so here you can easily calculate the angle of incidence, that is 41 degree, because 1 upon mu sin IC you will get as 1 upon mu. 1 upon 5, 1.524 in the is equal to 0.6542, and if you find this value from natural sine table, then you will get 41 degree. So R1 plus R2, as you know, R1 plus R2 is A. So R1 is A minus R2, 60 minus R2, R2 is IC, that is 41 degree. So R1 is 19 degree. Now according to Snell's law, for the first phase, try to understand, at this phase we are applying the Snell's law at this phase. So sin I is equal to N1 sin I is equal to N2 sin R1. N1 sin I is equal to N2 sin R1. So we just have to place the values. Okay, N1 is 1, that is refractive index of air is 1. Okay, N2 is mu, that is refractive index of the prism. Okay, so N1 is 1, so 1 sin I is equal to mu sin R1. Mu is 1.524, sin 19, just we have to look into the table of natural sine, you will get 0.3256, and if you multiply these two, then you get 0.4962 approximately. Okay, and 0.4962 is approximately 0.5. So incident angle 0.5 is nothing but 30 degree. So incident angle has to be 30 degree around. Okay. Now a card sheet divided into squares, each of size 1 millimeter square, is being viewed at a distance of 9 centimeter through a magnifying glass. Okay, of focal length 9 centimeter held close to the eye. What is the magnification produced by the lens? How much is the area of each square in the virtual image? The area of each piece is given, that is 1 millimeter square. Object distance u is equal to minus 9, focal length is 10 centimeter. So first we will get the value of v, that is minus 90 centimeter, and therefore magnification is v upon u, just value of it, that will be 10. Okay, so area of each piece in virtual image. Okay, because 1 millimeter square is the area, so length will be 1 millimeter, breadth will also be 1 millimeter. Now magnification is 10 times. Okay, so 10 times its length is increased, 10 times its breadth is increased, so its length of the square piece and breadth of square piece will be 10 centimeter in the image, 10 millimeter rather, 10 millimeter in the image. So 10 into 10 will give you 100 millimeter square, or we can say 1 centimeter square will be the area of each piece in the virtual image.